Hello, my name is Reed,
I'm Thomas.
and we'll be going over our TR MIPS 32 Enhanced SIMD architecture. So we're going to start with an overview, and just to give a little background for our name, TR Thomas Reed just stands for our names, the MIPS 32, which is the base architecture that we're going off of, and then Enhanced SIMD is our enhancement, which is single instruction, multiple data is what SIMD stands for, so that was our main enhancement. We did a couple other smaller additions, but that is our main one, so that's our name. And so we'll be going over the MIPS overview of just our general ISA, and then we'll talk about our enhancements and future enhancements. So the base stuff that we'll be going over for general MIPS architecture is our memory architecture, our register sets, our data types, addressing modes, and instruction set. So first off, we have our memory architecture, which is a Harvard architecture, separate memory modules for our instructions and data, which is against the von Neumann. And then it's more efficient than the Princeton architecture. Sorry, not von Neumann. And our memory is formatted in big endian format, as previously discussed, with 1K by 32-bit data memory and I/O memory. And you can see the big endian format up here. And our main CPU register file is 32-bit data values. So our register set that we've gone over before, we have 32 CPU registers. PC and I registers are not used by the programmers, but we just want to include them, that we do use those registers. And then we have our R0 as our constant 32-bit zero values. We have our stack pointer, which again points to the stack, and we have our return address, which is used for coming back from interrupt when we don't use a stack pointer, and then our jump and link. And then so here's just the description of all of the 32-bit CPU registers in a general MIPS format. We didn't use some of these for like reserved for OS kernel. We just used them all as general, besides the stack pointer, return address, and zero. But these is what they would be used for should we have implemented it more exactly. And so our data types, we have our 32-bit signed and our 32-bit unsigned data types. The range is obviously negative 2 million to a little bit over 2 million for the signed, and unsigned is 0 to 4 million. And then we have extra data types for our enhancements, which we'll get to later. So our addressing modes, we have register, which operands are obtained from the registers in the CPU, i.e. we use add and sub. So those kind of operands use the register values. We have register indirect, which is used for load word and store word, where we are obtaining, we're doing the effective address calculation and then getting the operands from memory. And then we have our immediate, which are generated from the immediate trailing word, which is the 16 bits that we will sign extend, or however we generate the value with the 16 bits, which we use in add immediate and jump and other of those types. So then here's our base instruction set, where we have our R type, 0 for the opcode, RS, RT, RD registers, our shift amount, and our function select, and the immediate similar opcode, 2 source registers, our immediate value, and then we have our opcode for the J types, which are jump and link and jump, and then 26-bit immediate. And so now we're going to go over the some of the hardware for our design. So we have our test fixture, test module, which instantiates our CPU, our data memory module, and our input-output module, and then we have our interconnected buses for data and the addresses. And so now we're going inside the CPU, our main module. We have a control unit, we have our instruction unit, and our data path, and they're all interconnected, sharing the PC values. They go to the data path, and then we have our flags and our different control signals going from the control unit to the data path. And so now we're going to go over our enhancements. So the first thing is the SIMD, single instruction, multiple data, which we have new data types for, new instruction sets for, and then we have a couple of hardware additions, and then we have a couple smaller instructions that we'll go over after that.
So for our SIMD enhancement, we added a new vector data type, which gives us 2 more data types, 8-bit and 16-bit vectors. So how this works is we take our 32-bit register and then we make it represent either the 4 8-bits or the 2 16-bits, depending on the type of vectors we're using. And when we're doing operations or instructions, what happens is when we take the 8 bits of the first operand and then a specific 8 bits of the second operand to get the specific bits of the destination, such as if you take the 31 to, well, this type, so it's 31 to 24, and so, yeah. When we're doing the vector operations, there are no flags, so except for the 0 flag, but in that case, all of these vectors would have to be a 0. And then this is our addition to our integer data path. We added a vector AOU, which is basically a duplicate of the AOU. It takes the same function select and ship them out. The only difference is the concatenation of its inputs and the SIMD select from the controller unit. And using this SIMD select, we choose either the 8 or 16-bit vector type, and it also decides whether this new mux that we created will take in the data from vector AOU or the original AOU.
Mm-hmm.
So this is our instruction type for the vectors. For vector 8 bits, we check for the first 5 bits. There's a 2C for 8 bits and 2D for the 16 bits.
So those were never used for some kind of I-type instruction?
No.
Are you sure?
Yes.
Because that's why we chose 1F, which was an unused opcode. And then you'd have to put like the 2C down at the function select or something like that. I think that's not, I think that's used, 2C and 2D. They're not free to use.
All right. Well,
In other words, those are I-type or J-type opcodes. So our enhancement was supposed to put a 1F up there, and that would trigger that you're doing like an SIMD instruction, but so you're using the function select for your type of instruction.
yes.
Yeah, somehow you'd have to combine the two. Somehow.
We could probably.
2C is not available to use, neither 2D.
Yeah, so we probably could have reduced the amount used for the shipped amount.
To be clear, we never used 2C this semester with our limited subset. But as far as if this is going to be compatible with MIPS, you can't use 2C or 2D.
All right.
Yeah, so that's what I meant. Yeah. So it'd be just a little bit of fudging your opcodes. Wouldn't change the hardware whatsoever. So we'll consider that your hardware works great. So it's function select that you're going to do the different types of SIMD. Okay,
Yes.
we're good.
So this is our vector AOU. So it's basically the same as our original AOU, barring the multiple flags except for Z. The modules in here have a concatenation of the S and T from the register. And this would be an example using division. So what we did was concatenate like the 8 bits for the specific vector to get the quotient. So the difference between the quotient and the other instructions is we still use the high and low registers, but So for the high, we have each of the remainders in this specific register, and then for low, it takes in all the quotients of the vectors, which is the same as for 16 and 8. For multiply is a bit different because when we multiply the 8 or the 16, we'll get double the amount of the bits. So for 8 multiplied by another 8 bit, we get the 16 bits. And so basically, we get the A1, B1 will give us product 1, and then A2, B2 will give us product 2, and then so forth.
Mm-hmm.
And this is our verification for our specific instructions. When we're doing the add instructions, the difference between the add 8 and 16. To know that this works, we loaded R1 and R2, and then use these two registers to compare the difference between the different adds.
Mm-hmm.
Here you can see that the carry doesn't affect the 5, or yeah, it doesn't affect the first byte or the upper byte of this register for number 3. And then for the 16, you can see that there's a 6 here instead of 5 because of the carry from the F plus 5 up here. And then we have a multiply 8 and a multiply 16. Well, yeah, we have the 16-bit values. And for the multiply 16, we have the 32-bit values for the low and the high.
Mm-hmm. That's good.
Okay, then we also created a shift for the shift left logical and the shift left 16. So our original modification is shifting the first register, register 1, which is a repeat of AF. Because we lose the 1 that is from the 8 bits, we get a repeating 5E instead of 5F. And then you can look at register, you can look at shift left logical 16 and see that we get 5F, 5E because one of the bits is dropped out from the previous A right here. And then it's pretty much the same for the rest. Shift and
So you did do a barrel shift on all the SIMD shifts?
yes.
Excellent.
And then we have the logical operations, but they pretty much remain the same because there are no carries and they would look normal,
Yeah.
irregular.
Yeah.
Okay, so now, just for the additional, smaller enhancements that we made, we have a pre-decrement push, where we're basically loading in or pushing to the stack the value at RT, pre-decrementing the stack pointer first. So pretty just a general pre-decrement push. And we have our post-increment pop just as the counter to that, where we're incrementing, well first we're pushing to RT the data at the stack pointer, and then we are incrementing after.
Can you back up just one on your push? Does the RT register have a load enable on it? So like you say on the first step, you're loading RT, and then you're not using it till the 3rd clock. So what happened to RT on the 2nd clock if you don't have a load enable to protect it during the 2nd clock? Like RT, I assume, is being written on the 2nd clock also. What would it be being written with? So the first two clocks, you're calculating the address by decrementing the stack pointer, but you show RT being written on the first clock but not used till the third clock. You know what I mean?
Yes, I'm sorry, I'm trying to remember. I think, throw it back in.
So
Sorry.
it's actually being written again on the second clock, you think?
Yeah, I think I might have missed a little bit of the RTL.
Okay,
Sorry.
but those would be the 4 steps, no doubt. Okay, thanks.
And then the pop is just reversing back basically and putting the data at the stack pointer onto RT and then post incrementing.
Good.
And then we have the additional states. So we have our move, which these are all 1 or 2 additional states. So we just have our move 1 and 2, clear 1 and 2, no op, and then we added rotate left. and
Rotates are
rotate right.
good, that's good.
So we just added that logic into the barrel shifter, just change bit manipulation. But so those were our additional single or 2 state enhancements.
To be clear, however, no customer is gonna wanna pay for the additional hardware that it would take to do instructions that could be done, just to be clear. But the rotates, yeah, put them in there. We need rotate.
So now we're just going to take another look at our integer data path, just recap how we had our 2 ALUs in parallel, so we could do the SIMD or our normal ALU operations. And we just had the SIMD select again to switch between the operations, whereas all of the additional, the push, pop, move, clear, and all of those were in the normal ALU, so we didn't implement those into the vector ALU. But so that would be our final integer data path. Okay, and so now we're just going to talk about our future enhancements. There was more potential with our SIMD, single instruction, multiple data. Could add more instructions and data types. There's quite a few, just adding different varieties, more instructions. We had attempted in the beginning to work on pipelining, but we're a little bit discouraged after the first weekend, so we did not, but we'd like to give another shot, hopefully. And we did also talk about floating point unit, and then some single instructions that we added would have been swap and negate. So those were our future enhancements, hopefully. Any questions?
Excellent job, good job.